Hello everyone and welcome back to another video. Today I wanted to make a part 3 or the final part in my introduction to mathematical proof. And now that we've gone over logic and gone over set theory, I think we can finally get into actual proof techniques and start to go over just a bunch of examples of how these techniques work so you can get a better grasp of them. But before we jump into the specific techniques, I wanted to start by introducing a concept that exists at kind of the intersection between logic and set theory, and I forgot to put it in both of them, so I wanted to go over that quickly here just so you guys are familiar with some of the notation. And that specific concept is the concept of quantifiers. So in mathematical notation, you see these two symbols, or this symbol and this symbol. This is like an upside down A, this is like a backwards E, and basically this one means for all, and this one means there exists A, or there exists. And additionally, you'll sometimes see this symbol, this E with an exclamation mark. That means there uniquely exists. So basically, what these are kind of at an intersection between logic and set theory, because they refer to they typically come in the form of a claim like this, where it's like for all x in a set, proposition P is true. So we get propositions from like logic, and then but it's discussing specifically all elements in the set. So for all elements in the set, proposition P holds. That's how you read that for all statement. And then additionally, you have this there exists, and this would basically mean there exists an element within A where P is true, and then to say there uniquely exists would be saying there uniquely exists, there only exists one element in A where proposition P holds. So just for some examples of this, one example would be for all n in the set of all integers, 2n is even. So basically all this is saying every single integer, whether it's -1, 1, 2, a million, you multiply it by 2, that number is even. That's all this is saying. So it's for every element within the set of all integers. Another example where we use the there exists, we have there exists an there exists a subset of the naturals where the size of the subset is 5. And this is a pretty trivial claim. Basically all it's saying there exists at least one subset. So for example, you find one example and you prove the statement true. So there's example 1, 2, 7, 9, 12. And all this means is there is a subset of natural numbers where the cardinality of x is 5. And this is a subset of all of the natural numbers, and the cardinality is 5. Or cardinality is just the size of the set, the number of elements in the set. And then additionally, along with this, we have these concepts. There's also their negations. So if we wanted to say it's not the case that for all x in A, P is true, the negation of that is that there exists an x in A where P is not true. So like if we wanted to negate the statement above this for all, if we wanted to negate this statement, It's very hard to draw on these sometimes. If we wanted to negate this statement, we would have to find some natural or some integer where 2n is not even. And you won't find that, but if we wanted to show that that is false, we show that the existence of at least one. Additionally, to negate there exists quantifier, all we'd have to do, or what we'd have to do, is show that for all x in A, P is not true. So basically, to show that there does not exist an x in A where P is true, you have to show that for all x in A, P is not true. So basically these quantifiers are kind of negations of each other in that sense, or they show how you would negate the other one. Okay, so that's just a brief overview of quantifiers. You'll sometimes see these notations in proofs and just in mathematical logic. You'll sometimes even see philosophers use these, which once you get into that level of philosophy, that is beyond me. But I mean, I can read the words that they're saying, but it's more I know recognize this from math, but you do see this in all forms of different like logical applications when people are talking about logic. But okay, so with that, let's go into next. We can go into a brief introduction into what theorems are. And basically, actually, I'll just do a face cam for this one because I'll just explain this without needing the notepad. A theorem is basically just a mathematical statement that is true and must be proven true. So not something that is like an axiom. It's not something that is arbitrarily true, not something that we just accept. It's something that's true and that we have to prove true. And typically, a theorem takes the form of if A, then B. So if you remember from the video on logic, that's called a conditional statement. And if you remember the truth table from that, we'll go over all of that in this video again too, just as a recap. But it takes the form typically of if A, then B. And then sometimes you'll also see biconditional statements. That's why it was important that we went over those as well. And that's just A if and only if B. And a proof is just basically a written verification that shows that the theorem is definitely unequivocally true. And we also use definitions quite a bit in math to give us exact, unambiguous meanings for mathematical terms that we use in our proofs. So you'll see like things defined all the time in math. And then other terms that you'll often hear are proposition, and this is kind of used interchangeably with theorem. Theorems, typically when people talk about theorems, they're referring to more significant propositions, while propositions are more just used as like a default standard of like, this is something that we're trying to prove true. That's just generally how I've seen them used. Like often when we're proving stuff here, I'll say proposition instead of theorem. Additionally, a lemma is a theorem whose main purpose is to prove another theorem. So sometimes in the process of making a proof, we cite other theorems, we cite definitions. So a lemma is just something that we use that we prove in the effort to prove something else. So it's like a smaller step in the main process. And a corollary is just a result that's an immediate consequence of a theorem or proposition. And there's no need to really memorize these terms. You'll start to understand more of what these mean when you see them in context. But yeah. Okay, so to begin with, now let's actually jump into proofs. So the first method of proof that I want to go over today is the simplest, easiest to understand proof, and it is just direct proof. And direct proof is typically used for proving conditionals, so if A, then B, or if P, then Q. So just remember from before, the way that we kind of set up this truth table, we have P, Q, the way this was set up is if P is true and Q is true, then P implies Q is true. If P is true and Q is false, then P implies Q is false. And then the cases where P is false, regardless of what Q is, we say that P implies Q is true. So given that when P is false, it doesn't really tell us anything about P implies Q, the way that a direct proof starts is by assuming that P is true and then trying to, or is only concerning ourselves with situations where P is true, and then whether or not that forces Q to be true. Because if you can show that whenever P is true, Q is true, you've proven that if P, then Q. It follows naturally from the English, and then it also follows naturally from the truth table, because those correspond to each other. So the basic form of a direct proof is this. So you have a proposition which takes the form of P, if P then Q. And then you have a proof. And the way the proof works is you start with suppose P. So you assume that P is true. Let's make sure I spell this right. And then you do a bunch of steps, and this is where like the actual like art of the proof kind of comes in. A lot of this is stretching more of your creative brain at like how can you put these definitions together and use this logic together in order to get from P to therefore Q. And that's where people actually start struggling with math, because a lot of times people who get into math there's a very like linear way of thinking. People love math for its like very linear thinking. There is a right answer, there's a wrong answer. But a lot of times people struggle when they start coming into proofs, because a lot of proof requires creativity. You have to come up with some way to arrange these, to arrange all these definitions and concepts and lines of logic together to get from P to Q, and that's not told to you beforehand. You have to come up with that kind of on your own. And a lot of times people who are good at math growing up start to struggle with proofs because they can't get their mind to start thinking in terms of like in a more creative way, sort of. But that's kind of a tangent. But so at the end of the proof, people put like QED, or they put this black square, and that just signifies the proof is done. It's been proven. It's the proposition is true. And because of this logic, that means that this proposition is true. If you suppose P, go through the mathematical steps, and then you get to Q at the end, then you've proven the proposition true. You can move on. So you add that big period because it's a very satisfying way to complete, I guess. It's very satisfying to complete a proof. So you add an extra big period because you really want to emphasize that you're done. No, I don't know. But so with this, let's actually get into a proof. And before we do that, let's give some definitions just so you guys are aware of the way that things are defined and have like a precise definition. And this should be a definition you guys are aware of. An integer n is even if n equals 2a for some a in the set of all integers. So that's just this is a more formal definition of even than probably what you were taught, but this is very helpful in proofs. And it's equivalent to like the sort of very intuitive definition that we typically have of even and odd, where it's like 1, 3, 5, 7, all those are odd, and then like 2, 4, 6, 8, 10, 12, all those are even basically. This is equivalent to that. This is just a more formal way to write it that's more helpful in proofs. So these are definitions of even and odd, and with this, let's go into our first example. So here, what we want to do is prove the proposition if x is odd, then x squared is odd. And the proof of this, based on this direct proof, if I can spell, based on the direct proof that we laid out earlier, or just the general outline. So we want to start by assuming p. So in this case, p is x being odd. And then we want to get to q. So in this case, x squared being odd. So what we start with, we're going to suppose and x is an integer, is odd. Then x equals 2a for some, or sorry, 2a plus 1 for some a in the set of all integers. And then that means that x squared equals 2a plus 1 squared. And if you remember from high school math how to FOIL these out, this will be 4a squared plus 4a plus 1. And then from there, this is where a little bit of creativity comes in. You can pull out this 2, and then we have this value in here, and this is an integer. And we know that because just a basic fact about integers is that when you add together two integers, it stays an integer. When you subtract two integers, it stays an integer. And when you multiply two integers, it stays an integer. And since all we're doing here is multiplying and adding integers, the result is still going to stay in the set of all integers. Now, so what this means is that x squared takes the form 2 times some integer. Let's call this b actually. We'll say this equals b. 2b plus 1. So it's 2 times some integer plus 1. And here we see that the definition of something being odd is 2 times some integer plus 1. And we use that definition here as well. But what we've shown is that x squared fits that definition of an odd number. So x squared is odd. And because of this, we've made a direct proof that if x is odd, then x squared is odd. We've proven now that this proposition right up here is true. Every time x is odd, as we've seen, it implies necessarily that x squared is also odd. So that's how that direct proof works. Okay, so with this out of the way, let's go into another type of proof, and this is also for proving conditional statements. Let's block off this area. It's always fun trying to preserve space for these things. I really want to make sure that I'm saving enough room for me to do all the rest of the stuff that I want to do in these videos, but we shall see at the end how all of this turns out. And if anything, I can always just expand the page a little bit, to be honest. Okay, so the next type of proof is contrapositive proof. And this type of proof is based on the fact that that P implies Q is the same. It is logically equivalent to not Q implies not P. So I'll write that out. So the reason why this proof works, and the entire foundation of this, is based on the fact that not Q implies not P is logically equivalent to P implies q. And this makes intuitive sense, because if you know that if p is true, then q is true, that also seems to imply that if you know that not q is true, that also means not p is true, by that same sort of truth table logic, and then basic intuitive sort of logic on how the situation works as well. Because if we found out that p was true when not q, when we knew that not q, or that q was not true, and found out that p was true, then that would show that p does not actually imply q. Hence, these two statements are logically equivalent. I would recommend you write out the truth table on your own and kind of think more about some of the intuition behind this logic to more fully kind of understand why this works. But the fact is, it does work, and that's sort of the basis for contrapositive proof. So, to see a basic outline again, the way that this works, we have the proposition, and in this case, again, we are using the conditional statement, and we can prove this true by supposing not p or not q, therefore not p. And that would be a proof. That would be a proof of that conditional statement. So for a sort of similar example, I'm going to try to stick with using odd and even for the rest of this video, just so we don't have to get into a bunch of other number theory definitions and stuff like that that I'm hoping to get into in more of a number theory course that I want to put up on this channel. So yeah, we'll start with this. The proposition is this. Suppose x is an integer, then we have if 7x plus 9 is even, then x is odd. And to prove this statement, we're going to start by supposing that q is not true. So in this case, x is odd is q, 7x plus 9 being even is p. P, then q. But here we're going to start by supposing not q. So we're going to suppose that x is not odd. And if x is not odd and it's an integer, x is even. So x is even. Thus, by the definition of an even number, x equals 2a for some integer a. This means that 7x plus 9 equals 7 times 2a plus 9, which is the same as 14a plus 9. And then this, we can keep going, and simplifying this further, is 14a plus 8 plus 1. And the reason we're doing this is because we're going to take a 2 from this 8 and this 14, so we're going to have 2 times 7a plus 4 plus 1. And here, this is an integer. So what this means, since we have 2 times an integer plus 1, this means that by the definition of an odd integer, 7x plus 9 is odd. which is the opposite of what we were trying to show. 7x plus 9 is even. So this means that (7x plus 9) is not even. And this is the end of the contrapositive proof. So what did we just do here? We started with the idea that the integer is not odd, so q not q, and we showed that 7x plus 9 is not even, so not p. This follows the logic of the contrapositive proof. It's a direct proof of a logically equivalent statement, or it's a contrapositive proof of the original statement. So what we have here is a proof that if 7x plus 9 is even, then x is odd. We have the proof by the contrapositive approach, supposing that x was not odd, and then proving that if x is not odd, then 7x plus y is not even, which means that if 7x plus 9 is even, then x is odd. Those are logically equivalent statements. Okay, so with that out of the way, we can go into our next proof technique. Let's block this out. Which is a proof this is going to be our first proof technique that is not only for conditional statements. And this proof technique is called proof by contradiction. And the basic way that this technique works is by proving that, so we're trying to prove a proposition P, right? We'll say P is what we're trying to prove. We start by assuming not P, and we show through direct proof that that leads to C and not C. And C could be any other proposition in the world. All it's trying to show is that it leads to some contradiction. It shows us that C and not C are true at the same time. And one thing to note here is that P is logically equivalent to not P implies contradiction, C and not C. And kind of the reason why that is because P is either true or false. That's just what a mathematical statement is. P is either true or false. There's no middle ground. This is the law of excluded middle. It's true or false. There's no middle ground. So if you can prove that not P implies a contradiction, it means that P is true to begin with. So the way that these sorts of proofs work, you show that basically not P leads to absurdity. It leads to some sort of nonsense. And the way that these sorts of proofs work, you have your proposition, P, and then a proof, suppose not Q, ... and then therefore, or sorry, suppose not P, sorry, and then continue in your proof, and then thus C and not C. So that's the basic structure, and a lot of times these sorts of proofs end up looking like contrapositive proofs. So a lot of times you can find a simpler version of this proof with a contrapositive, but that's not always the case. Sometimes proof by contradiction is useful on its own when you don't have a contrapositive equivalent, and it's super useful compared to those because it's not only useful for proving conditional statements, it's useful for proving any statement whatsoever. But to start, let's focus on how we can use this proof to prove conditional statements. And before we do that, let's recall that the negation of a conditional is P and not Q. So for the sake of our proof, we're going to do another example proof using odd and even numbers, just for simplicity's sake, so I don't have to introduce a ton of new concepts in this video, since we're already introducing enough new concepts with all these proof techniques. So that's the negation of the conditional, and our statement is going to be, suppose A and Z. So then the statement is, if A squared is even, then A is even. And the proof for this statement, we're going to start by suppose, for the sake of contradiction, that the negation of this original statement, so the negation would, so this is P, A squared is even, and this is Q, A is even. The negation of this would be P and not Q. So A is even, and A squared is even, and A is not even. So A is odd. Thus, A equals, we'll say 2k plus 1. The specific letters that you use don't matter. I know that in the definition I think I used A, but for some, they're just stand-ins for the concept. So that means A is 2k plus 1. So this means then A squared equals 2k plus 1 squared equals 4k squared plus 4k plus 1, which equals 2 times 2k squared plus 2k plus 1. And this is an integer. So this means is even, or sorry, is odd. So A squared is not even. Thus we have, therefore, A squared is even and A squared is not even. Because remember from above, we originally assumed that A squared was even, but here we also have that it's not even. This is a contradiction. And that basically ends the proof there. But if we wanted to continue, we could write out, so we have a contradiction which implies that A squared is even implies A is even is true. And that's the proof. All you have to do there is show the contradiction, and then you show that the negation leads to contradiction, so the original statement is true. Yeah, okay. So that's it for that proof. And now we can go ahead and show you all how we would prove, oh shoot, I didn't have my correct heading up there, that's fine. We will, so that was proof by contradiction. I had the wrong heading up, but that is a-okay. I don't know what I'll do. I'll post a comment about that in the comments and then pin that. But up next, after proof by contradiction, we have proving biconditionals. And the way that we would prove a biconditional, if you remember, a biconditional is P if and only if Q, and this is logically equivalent to if P then Q and Q then P, if P then Q, and if Q then P. And this is the most common way to prove this is by using that statement, because logical equivalence always implies that if you prove one, then you prove the other. So the outline for this is this. So you have the proposition, and then the proof would be prove P then Q, and you can use contrapositive, you can use by contradiction, you can use direct. Go ahead, do whatever you want, and then you prove Q if Q then P, and then that completes your proof. And you can once again prove by direct, contrapositive, any type of proof, by contradiction, any type of proof that you want to do. Okay, so let's do an example here. So for here, let's use the proposition. Suppose n is an integer let's do it like this. N is odd if and only if n squared is odd. So this is the biconditional. If and only if is equivalent to this notation, and the proof for this will be as follows. We're going to prove each direction. So we're going to start by proving this direction. So we're going to start, suppose n is odd, so n equals 2a plus 1 for some integer a. Thus, n squared equals 2a plus 1 squared, which equals 4a squared plus 4a plus 1. I feel like we've seen this same thing being proven so many times here, but I think for the sake of example, it's helpful to get this sort of repetition to kind of see how this can apply to different situations. That's an integer, so n squared is odd. So that's one direction. And then for the other direction, I'm going to use a contrapositive proof. So what we're going to do is suppose, in this case, P would be n squared being odd, or I guess in Q in this case, so we're showing Q then P. Equivalent to if Q then P is if not P, then not Q. So we can start, suppose if, so you're going to suppose that not P, which is n is odd, then not q, which is n squared is not odd. N squared is n is odd, n is not odd implies that n squared is not odd. So basically the way this is going to work, we have P implies Q. So to prove this part, this direction, we directly prove. And to prove this direction, we prove that. So by contrapositive, that would mean that Q implies P. Since those are logically equivalent statements. Okay. So n is even, so n equals 2b for some b in the set of all integers. Thus, n squared equals 2b squared, which equals 4b squared, which equals 2 times 2b squared. That's an integer, so n squared is even, which implies n squared is not odd. And that is our biconditional proof. So fun. So sometimes these biconditional proofs can be pretty long, pretty tedious because you have to prove both directions, but in the end, we did it. We're incredible. We know how to prove math statements. Look at us. Okay, so fun. So next, I might have enough room actually. Yeah, I think I do actually. Let's do this. So let's talk about the concept of using cases. So sometimes to prove a statement true, we have to split our proof into multiple cases. So let's just, to understand this, let's use an example. For all n in the set of all naturals, 1 plus -1 to the power of n times 2n minus 1 is a multiple of 4. And then just for a quick definition, because we're using a new term here, it being a multiple of something, I'll just define that very quickly. And the basic definition for something being a multiple of something else, you have for A, B that are natural numbers, or I guess integers could work here too. Let's use integers because this is the way that I've seen this definition. But the naturals are a subset of the integers. So B is a multiple of A if B equals AC for some C, for some C in the set of all integers. Very fun. Okay. So, for our proof of this statement above, we are going to split the proof into two cases. So, you're going to suppose that n is a natural. So, n is either even or odd. So our first case, we're going to suppose that n is even. So n equals 2k for some integer k. Oh, so there's these little buttons on my pen, so sometimes when I click them, it just does some chaotic stuff accidentally. Okay. Also, since n is even, -1 to the power of n is just 1. Basically, the way that this sort of function works, it just flips from -1 to 1 to -1 to 1, because so you start with -1 to the power of 1, that's just -1. Multiply a -1 becomes a 1. So for all, and then multiply by -1 again, it becomes -1 again, and then keep doing that, and it switches back and forth, and it forms this pattern where, depending on whether n is even or odd, the function evaluates to 1 or -1. In this case, since n is even, it evaluates to 1. So we have that. Thus, n thus 1 plus -1 to the power of n times 2n minus 1 equals 1 plus 1 times 2 times 2k minus 1, which equals 1 plus 4k minus 1, which equals 4k. And 4k is 2 times an integer, because you could take that, or no, sorry, 4k is directly just the number, this integer here, or this integer is just 4 times some other integer. K is an integer, so this is a multiple of 4. So then for case 2, suppose n is odd, so this covers all other cases for n. So n equals 2k plus 1 for some, actually I'll use a different letter, just to be, oh, what am I doing? Let's not do that. So n is 2a plus 1 for some a in the set of all integers. So we have that, and once we have that, we also know -1 to the power of n is equal to -1, kind of for that same logic we talked about before. Thus, 1 plus -1 to the n, 2n minus 1 equals 1 minus, because we have a -1 here, multiplying it by everything, 1 minus 2 oof, that's ugly. Okay, that is a mistake. Ooh. Two a plus 1 minus 1, And this ultimately evaluates to 1 minus 4a. The 2 distributes, so it goes to 2, and then subtract 1, so you have plus 1, which is negative 4a. And a negative of an integer is also an integer, so it still works out. So this is also a multiple of 4. And that is the end of the proof. Because we showed that regardless of whether n is odd or even, this statement still holds to be true. Yeah, you proved both. You proved it in both cases, so the overall statement is true. And then another type of thing that we often do with cases, if there's something, if two cases are entirely alike to the point where proving a second case follows identical logic to the first case, or there's just like a notation flip or something, we just use the phrase without loss of generality, assume this. So for a example of this, let's look at the idea of here, if two integers have opposite parity, so one is even and the other is odd, or yeah, the other way around. Then their sum is odd. So for the proof of this, suppose m and n are integers, and with opposite parity, and then in this case we can say without loss of generality, and you'll often see this written as WLOG. It's just without loss of generality, assume m is odd and n is even. So what we can do next, we just move forward with that assumption. So m equals 2a and n equals 2b plus 1, or wait, I switched them around. That's funny. Okay. So m is 2a plus 1. I just wrote them backwards. In my notes I wrote m is even and n is odd. But that's fine. I mean, the same thing applies. Without loss of generality makes it so that you can prove one, and that basically shows the other to be true. You have to be really careful with this phrase because sometimes people try to use it when you can actually drop generality in this context. But in this case you can, because all that would happen is you have an identical proof from the other direction. So then after that, we have therefore m plus n equals 2a plus 1 plus 2b. So then we have 2a plus b plus 1. That's an integer. So we have m plus n is odd. and that is the basic proof there. Okay, so with that, we could potentially move on to proof by induction, and let's actually make this significantly bigger because I am definitely running out of room. Okay. Okay, so now for my last section, I want to go over mathematical induction, which is going to be the final technique of proof that we go over in this video. And the way that mathematical induction works, it is used to prove an infinite number of statements, or an infinite list of statements true. Mathematical prove an infinite list of statements true. So we have just this infinite list of statements, prove them true. So the basic outline for how this works, we have a proposition, which typically will take the form of, like oftentimes it'll take the form of for all n in the set of natural numbers, Sn is true, or for all n in the naturals where n is greater than or equal to 1, for example, which sometimes people include 0 in the naturals, sometimes they don't, so I want to specify this when I'm talking about this, but sometimes it'll be greater than or equal to 0, it'll be stuff like that, but we'll just specify that here, like just for this example. Actually, we don't need to specify it. We'll just say for all n in the naturals, Sn is true, because it's the type of thing that we would often see. So a proof works through this methodology. So step 1 is our basic step, which basically in this step we prove S1 is true. Or in the case of strong induction, we have to prove a set of initial statements true. So we'd prove like S1, S2, up until like SK are true, for example. Yeah, or we could just say like up until SM. So these are initial statements. So then next, we have our inductive step. And in the inductive step, we go ahead and say that given any integer k, we prove the statement SK implies SK plus 1. Or in the case of strong induction, for strong induction, we are given k greater than or equal to m, and then we prove S1 and S2 and all of these statements up until SK imply SK plus 1. Right? I think I'm doing that notation right. Yeah, that's essentially right. But I think that's right. Okay. So given these, so this is strong induction. So to start, let's just do a basic proof with simple induction. This one should be quicker, let's hope. So the basic statement is proposition if n is a natural number, then 1 plus 3 plus 5 plus 7 plus all the way up to 2n minus 1 equals n squared. So for our proof, let's do it like this. We're going to start, once again, with this inductive step, or with the basic step. So we're going to say, so this statement here, basically, this is Sn. So this guy is Sn. So our basic step, we want to prove S1. So S1 is the basic idea that 1 equals 1 squared. Simple enough, that's true. 1 does equal 1 squared because you simplify 1 squared is just 1. So that's true. So we can move on to the inductive step. And with the inductive step, we're going to suppose k is greater than or equal to 1, and that k squared equals 1 plus 3 plus 5 plus 7 plus ... plus 2k minus 1. Now what we want to do is evaluate this statement when we add a term. So 1 plus 3 plus 5 plus 7 plus ... plus. So we're assuming sk here. This is sk. We're assuming k is greater than 1 or greater than or equal to 1, and sk is true. So next we move on. Oh, sorry. So here we have this statement, and this statement is equal to 1 plus 3 plus 5 plus 7 plus ... plus 2k minus 1 plus 2k plus 1. So what we have here, notice that this whole first part is equivalent to k squared. So we have k squared plus 2k plus 1, and this is all just equivalent to k plus 1 squared if you factor this out. So what we have here is sk plus 1 is true. So sk implies sk plus 1. Because now we have that this statement, when you have k plus 1 as the last term, becomes k plus 1 squared. And that is the proof by induction. Sometimes the logic behind these proofs can be a little bit difficult to grasp at first, but so the way to think about this is assume it's kind of like you can think about it through the context of climbing a ladder. So the two steps, basically, you have the first rung, and we need to first prove that you can get to that first rung. That's kind of what that basic step is. Now, when you get to the inductive step, you're proving that you're proving that you can always make this step. Once you're at k, you can always make this step. So inductive step. So you're proving both of these things true. So you're proving that you can get to the first rung, and that once you're on a rung, you can always climb to the next step over and over again. And using these two together, you know that you can always get higher on this ladder, basically, because you can get onto the first rung, and then now you're on a rung, so you can go to the next rung. Now you're on this rung, you can go to the next rung. So that's kind of how these two steps work together to basically show that you can get up the entire ladder of proof. And strong induction works on a similar sort of concept, but it's a bit more complicated. And I want to show an example quickly here, just to kind of illustrate how strong induction works as well, just so that we kind of understand what's even going on with that type of proof. So for this one, I want to try to make this the simplest possible proposition I can with this, but it still might be a little bit convoluted. Oh my gosh, I don't know how to spell proposi. Okay, so the proposition is, let me find her. It is any postage or more is possible using cent and $5 stamps alone. Now, to start, the way that this proof starts, we're going to do the basic step, but in this basic step, we're going to prove 3 initial statements, or initial conditions first. And then also this whole statement is, so SN is postage of n cents is possible. Okay, so with that little bit of notation out of the way, let's jump into the proof. So the basic step, we're going to prove S8, which is the first step on the, which is basically the first step on the ladder. So we're going to prove that one first. We're going to prove we can get on the first step. And in this case, all you need is a 3 cent and 1 5-cent stamp. And then for S9, all you need is 3 3-cent stamps, and you get 9 stamps. And then for S10, you need 2 5-cent stamps. Okay, so we have these basic things out of the way. We've shown that we can get on the first 3 rungs of the ladder. And now we're going to try to show that once we have at least these 3 rungs, and we have 3 rungs, or we have all rungs below k plus 1, below the next rung, then we can get to that next rung. So if we've got to all of the rungs below the next rung, k plus 1, then we can get to k plus 1, rung k plus 1. So in the proof, we're going to assume that all of these are true, and we're going to start like that. Okay. So in the inductive step, what we're going to do is we're going to let k be greater than or equal to 10. So we're assuming that the rung that we're trying to get to is greater than or equal to 10, because we've already shown that we can get to these 3 rungs. Or we're saying that the rung that we're currently on is something greater than or equal to 10, because that's what we're curious about. We're curious if we can get up to the next rung once we know that we're on a rung greater than or equal to 10. Or we can get a stamp worth greater than or equal to 10 cents. And for each 8 less than or equal to m, less than or equal to k, assume a postage, assume SM basically. We're going to assume that a postage of M is possible with 3-cent and 5-cent stamps alone. So we're going to assume that we've made it to all the rungs, including K, on that ladder. And now we want to prove that we can get to K plus 1. So for all of these rungs, it's true. Now, we can get, so this means that we can get exactly K minus 2 cents postage. With 3-cent and 5-cent stamps. So we can get K plus 2 cents, and now add on a 3-cent stamp. And now we have K minus 2 plus 3 equals K plus 1 cents postage. And this means that SK plus 1 is true. And that completes the proof. That proves that we can get any quantity cents of stamps with just 5-cent and 3-cent stamps. Because we're assuming that we can get at least the first 3, and then once we have those first 3, we can always just add on a 3-cent stamp to get to the next amount of postage. Say we want to get to 12 cents. Say we want to get to 12 cents. Well, we know we can get to 9 cents, so we just add on another 3, and that works out. Same thing with 11 cents. We know we can get to 8, we can add on another 3. And then say we want to get to 50 cents. Well, based on this proof, we know that we can get to 48 cents already. 47 cents. So we can add on 3 cents. We can get to 50. That's kind of how the logic of this proof works. And it's kind of that same logic of climbing the ladder, but it's a little bit more complicated because it's assuming the ability to get to all of the rungs prior, but the logic still works. But yeah, okay. So with all of that, I want to thank you all for watching one of my longer videos. These math ones are always longer, but I do enjoy making them. And I hope you guys enjoy it as well. They're not my most popular videos, but I enjoy making them, and it's something fun for me to kind of prepare and put together for you guys. But yeah, that's all for today, and I can't wait to see you all again next month when I start jumping into number theory. And yeah, so I'm really excited for that. Want to go into that, do some of those theorems, work through that book. That was one of my favorite classes during college, and it'll be fun to kind of revisit everything and look everything over. It'll be fun. It'll be fun to like remember all of that class. But with all that, that's all for today. I can't wait to see you all next month. If you enjoyed the video, please like. If you want to be notified of new uploads, I don't do math all the time. A lot of times I try to do philosophy or religion or stuff like that. I've spent a lot more time on religion lately, just based on interest lately. But I still am trying to really prioritize this math content and try to get that out once a month. So if you've enjoyed this content, please subscribe and support me on Patreon. If this is really the content that you enjoy, I can try to do more than once a month if this is really the content that seems to be that people seem to be liking and wanting to fund and donate to more. And if you want to discuss further, if you have any questions, please reach out on Discord. I'm not that hard to reach. Just join the Discord in the link and message me. And not always on Discord, but I should be able to get back to things at least within the next couple days. But yeah, I think that's everything. So thank you all for watching, and this was a long video, so thanks for sticking it out, and I hope to see you all in the next video. Peace.